let's take a look at the next portion of our solutions, acids, and bases unit, and this time we're going to look at some properties of our acids and bases. So we're going to look at the nature of acidic and basic solutions. Now notice we're talking about solutions, so we're still looking at dissolving an acid or a base into generally a solvent, generally being water. So we can test solutions for a pH or a change in color of litmus paper or pH paper. And in order to distinguish between molecular, ionic, acids, and bases, a conductivity test is also required. So based on our nature of acids and bases, we can do a pH test and expect a change in litmus paper. And we also expect there to be a conductivity of our solution. Now, we have a theory that I'll give you a reminder that Arrhenius stated. Okay, Arrhenius was the guy who kind of gave a generalization about what he thought acids and bases were, and he said that acids are substances that ionize in aqueous solutions to form hydrogen ions, or H positive, and we have bases that dissociate to form hydroxide ions, or OH minus. Okay, this is a widely accepted theory, but we have a more likely theory that these H positives, they are so attractive to our water molecule that it's actually bonded to that water molecule to form this new ion called a hydronium ion. So we now consider acids to be H3O positive. So we have this combination of a hydrogen ion and a water molecule to create the hydronium ion. So we now say that acids are substances that ionize in aqueous solution to form hydronium ions. Now that we know about sort of our general concepts of acids and bases, we can talk about pH and pOH. So how do we calculate this stuff? Let's just jump right in and take a look. So acids and bases. The higher concentration of our hydrogen ions, or in other words, hydronium ions now, okay, we call that H3O. Now remember, square brackets means concentration. So the higher concentration of our hydronium ions, the more acidic a substance is, whereas the higher concentration of our hydroxide ions, the more basic a substance is. So lots of H3Os, acidic. Lots of OHs, basic. So we also have this principle of water called water ionization. Now, water is kind of a weird entity. We see that water has a pH of 7, so it's a neutral entity, and it's not acidic or basic. So we know that it has no OH and no H3O, and it's a molecular compound, so we would expect no conductivity. But when we put a conductivity meter in, we see that there is a very, very small level of conductivity. So this means that there has to be a small level of ions in our water, which is really weird. And this is pure water, like not tap water that has ions that have been dissolved in like calcium ions or chloride ions, whatever it might be. This is pure water. So because of that, we have to have some level of these ions. Now, in this case, we can only have hydroxide and hydronium ions. Now, this is such a small amount of water that occurs like this, but essentially 2 out of every 1 billion molecules of water will collide at the right speed and at the exact right place to create a hydronium ion and a hydroxide ion. So we have these 2 water molecules that will come together, bump into each other, to form 1 molecule of hydronium and 1 molecule of hydroxide. Now, a conventional conductivity meter won't even recognize this level of conductivity. It has to be very specific, very specialized conductivity meter, but we do see this happening, and this is called our water ionization constant. Now, essentially, 2 out of every 1 billion is sort of the same as we have this water ionization constant, and we call that Kw, is equal to 1.0 times 10 to the negative 14. And that's essentially how often we get this reaction happening, where we have 2 water molecules creating our hydronium and our hydroxide ion. So that's just important to know in our relationship between our hydronium and our hydroxide concentrations. Now, if we're talking about a standard temperature and pressure with a solution, okay, we're looking at sort of the differences of our hydronium ions in our solution. So a neutral solution will have a hydronium ion concentration of equal to 1.0 times 10 to the 7. So we have hydronium as times 10 to the 7 moles per liter. Acidic is where we have our hydronium ion concentration. Now remember, the greater amount of concentration, the more acidic it is. So our hydronium ion concentration is greater than 1.0 times 10 to the negative 7. And a basic is less than times 10 to the negative 7. Now one thing to keep in mind, we're talking about hydronium ions, which is a principle or a property of an acid. Whereas if we were to talk about our hydroxide ion concentrations, which I'm just going to draw I'm going to say hydroxide ion. At neutral solutions, our hydroxide ion concentration is also going to equal 1.0 times 10 to the negative 7 moles per liter. In an acidic solution, our hydroxide ion concentration is going to be less than 1.0 times 10 to the negative 7, because now we're talking about how basic an entity is. So if we're talking about a base, it's going to be less basic than neutral. It's more acidic than neutral, which also means it's less basic than neutral. Whereas if we're talking about a base, we're going to have a greater concentration than 1.0 times 10 to the negative 7. So we can talk about hydroxide ion concentration as well as hydronium ion concentration. Now, essentially what happens is our hydronium ion concentrations changes so much. So we invented this scale called the power of hydrogen, or pH. Now, you've heard probably of pH and the pH scale, and we've talked about it once before in this unit, but essentially the pH is a logarithmic scale. And the negative exponent to the base 10 of the hydronium ion concentration is going to equal the pH. So only if we have a pH of 1.0 times 10 to the negative 7, this is a pH of 7. If we have 1.0 times 10 to the negative 6, we have a pH of 6. I can continue. 1.0 times 10 to the negative 5, I have a pH of 5. However, this is only when I have 1.0 times 10 to the negative exponent. Now, if I have any other digits other than 1.0 here, I do have to plug this into a formula or a calculator to solve for the pH, because it isn't going to always equal 5. It will only equal 5 if I have 1.0 times 10 to the exponent of 5. And we'll get into that. So essentially, we see that from a pH, now this is pretty cool, from a pH of 2, so pH of 2, let's go, how do I want to write this? pH equals 2, we have 1.0 times 10 to the negative 2 for my hydronium ion concentration. So this is moles per liter. Now if I jump to a pH, let's say of 4, our hydronium ion concentration is now 1.0 times 10 to the negative 4 moles per liter. So if I look at this concentration, let's convert this value to a digit that isn't scientific notation. So 1.0 times 10 to the negative 2, that means I move the decimal place 1, 2 spaces over, so I have 0.01 moles per liter. Okay, now our pH change is only 2 changes of pH, like we have pH of 2 and then pH of 4, so it's only 2 numbers on our scale. However, because this is a logarithmic scale, which means that we have a curved, like a logarithmic graph looks something like this, okay, our difference between 2 and 4 is actually pretty significant, because if I have 1.0 times 10 to the negative 4, I need to move this decimal place 1, 2, 3, 4. So I would get 1, 2, 3, 4. So our change in pH from 0.01 to 0.0001 moles per liter is a huge difference in value from when we compare it to 2 to 4. Our change in pH is actually, or our change in our hydronium ion concentration is actually huge. Okay, we have like a huge difference from 0.1 to 0.0001. That would be like comparing 1 to 1,000. Okay, it's a huge difference in what we're looking at when we compare these values. So let's take a look at some pH calculations. So here's some fun math, or I think it's pretty fun. And really, let's not say fun like this. This is pH math. It's fun. That's a chemistry joke if I've ever seen one. So the pH is the negative log, because we have a logarithmic scale, so it's the negative log of our hydronium ion concentration. So pH is just going to equal, and essentially you just plug this into your calculator, you click the negative button, you click the log button, and then you type in your concentration. So this is our concentration in moles per liter. Okay, now inversely, this formula is just the rearranged version of this formula, but because just like the opposite of adding is subtracting, the opposite of multiplying is dividing, the opposite of a log is 10 to the exponent. So because we have a negative log, we have 10 to the negative exponent. So when we're talking about mathematics, this is just a rearranged formula to solve for this. Now, because we're not all super math stars or super math geniuses, I've just given this to you, and this is one that you can write down or memorize to use throughout this unit, as well as you'll definitely see it quite often in Chemistry 30 as well. So our hydronium ion concentration is equal to 10 to the negative pH. So again, if we're calculating our moles per liter of our hydronium ion concentration, we can get that it equals 10 to the negative pH. So 10 to the exponent of negative 7.2 or whatever it might be. Okay, so we've talked about pH, and pH is kind of familiar to us at this point. We've learned throughout school about pH and things like that. But what on earth is pOH? Now, pOH is essentially the negative logarithm to the base 10 power of the hydroxide ion. Now, that's a lot of words for essentially saying that instead of calculating the pH for our hydronium ion concentration, we're calculating the equivalent, the pOH, of our hydroxide ion concentration. So essentially, it saves us a step. We're looking for how much hydroxide ions we have rather than our hydronium ions. So it's the exact same two formulas where we have our negative log of our hydroxide ion concentration, moles per liter. And again, I simply plug this in, negative sign, log sign, buttons on my calculator, equals the negative hydroxide ion concentration, some sort of numerical value that will be. Same with this. If we're looking for the concentration of our hydroxide ions, then we have 10 to the negative pOH. Now, pOH, essentially, our pOH scale is completely inverse of our pH scale. So, let me just jot that down up here because I don't have it there. If we have our pH scale, let's call this our pH scale. Okay. This is a pH scale. Okay, so here's 7-ish. Okay, we have 0 to 14. If we look at our pOH scale, it's exact same length. All it is saying is neutral remains the same. Neutral is still 7. But when we look at the pOH of a very, very basic substance, it's 0. And if we look at the pOH of a very acidic substance, it's 14. So this is an acid over here, and this is a base over here. So a base has a high pH but a low pOH, and an acid has a low pH but a high pOH. So essentially the scale is just inversed. Now, one more calculation or one more bit of math to take a look at is calculating either one of your pH or pOH. Now, based on the fact of our water ionization constant, which you'll learn a little bit more about in Chemistry 30, okay, we have that your pH plus your pOH will equal 14, and that is simply because we have the inverse of these scales. Again, if I have, let's just put this in here, what color can I use? Well, I'll use green. If I have a pH of, let's say, 2, okay, my pOH is the difference between 14 and 2. So I can say my pOH is going to equal 14 minus 2. So it should equal 12. So I have 12 plus 2, which will equal 14. Now, if I was to look at my scale, I could just calculate that, and that is simply based on my pH scale, and that's all from my water ionization constant. So if I have my pH of 7, let's not use 7 as an example. Let's go with 5. 5 plus x equals 14. So if I was needing to solve for my pOH to do sort of a preliminary calculation, I would say, well, 14 minus 5 is equal to x. So therefore, your x should equal what? It should equal 9. So x, or your pOH, let's call it pOH, your pOH should equal 9. All right, so there's another calculation that we can use to solve for our pH and pOH. So let's just look at some calculations to solve some of these entities. So if I have a pH of 2.4 and I'm looking for my hydronium ion concentration, I simply go my my H3O is equal to 10 to the exponent of my negative pH of negative 2.4. So I simply plug that in. I go 10 to the exponent of negative 2.4 is equal to 3.98 times 10 to the negative 3 moles per liter. That is as simple as it is. I literally only need to plug in one variable for each calculation. Now, if I was to say, what is my hydroxide ion concentration, or no, let's go with, let's keep that here. We'll go with our hydroxide ion concentration is equal to, let's go with 2.6 times 10 to the negative 7 moles per liter. And we're looking for our pOH. To solve for this, I go, my pOH is equal to the negative log of my hydroxide ion concentration, which is 2.6 times 10 to the negative 7. So when I plug in my negative log, literally I just click the button negative, the log button followed by that, and then I go 2.6 times 10 to the negative 7. This equals my pOH of being 6.59. 6.59 is my pOH. Now, if I was to say, hey, you've calculated your pOH, what is your pH? From here, what is your pH? So I would say, well, if my pH plus my pOH is equal to 14, then I can say 14 minus my pOH is equal to my pH. So I can do that calculation. I can go 14 minus my answer from above. So my 6.59 is equal to, my pH is equal to 7.41. So that is as simple as these calculations are. Now there's a variety of calculations, and essentially I can ask you to solve for your the pH. I can give you the pH, and you can solve for your hydroxide ion or your hydronium ion concentration. I can also have you calculate your pOH, which you can then calculate your hydroxide ion concentration. So I can give you one variable, and you can solve for the remaining 4 variables, being pH, pOH, hydronium ion concentration, and hydroxide ion concentration, which is pretty cool. So one last thing to look at. You have these things called acid-base indicators, and acid-base indicators are essentially substances that change color with the acidity of a solution. Now we have a variety of acid-base indicators, one of them being red cabbage juice. Now if you have a chance, boil up some red cabbage and take it in and test the acidity of different solutions, and you will get a pretty cool color change based on different acidities. So we have acid-base indicators. Now these things are generally, it has 2 forms, and the 2 forms that they exist in will either will depend on how acidic a substance is. And you will learn a great deal more about really what acid-base indicators are in Chemistry 30. Now, pH test strips are also a universal indicator, and that's what that red cabbage is. It's a universal indicator. But we have other specific indicators that you can take a look at in your chemistry data booklet. So let's just jump over. Let's scroll through some pages here in your chemistry data booklet. It's towards the end of your booklet. I can't remember exactly what page it's on here. Oh, here we go. So here's your acid-base indicators, and here's a list of several acid-base indicators that you may have in your lab. And essentially, what you see here is that it will show you the type of indicator, and it will show you the pH range where that indicator will change color. So if we have methyl violet, we get a pH range from 0 to 1.6, so very acidic. Okay, we would get a pH change from the 0 range that would exist as a yellow color. As it changed to a pH of 1.6, you would get a color change to blue. Whereas if you had something like bromocresol green with a pH of 3.8, you would have a yellow color. To 5.4, you would get a blue color. Again, if you look at something like phenolphthalein, phenolphthalein has a pH range of 8.2 to 10. 8.2, it's colorless, where a pH of 10, it's pink. So it's pretty cool that these things will actually change color. You get some sort of color change, chemical reaction, to see what pH range you're dealing with. So if you're dealing with some sort of reaction where you're trying to get your pH to go from say a 6.6 to an 8, you may want to use phenol red to see when you have reached that new pH change, whether it be from 8 to 6.6 or 6.6 to 8. Either way, you can add an indicator to your reaction, and generally it does not affect your reaction. It just will show you where so much about your reaction and what pH you're at. Now, one thing you might want to do is take a look at your acid-base indicators. There's, I believe it's a lab-based assignment that will show you how to use acid-base indicators, and it will give you an idea. It will give you 3 sort of acid-base indicators that are used to determine a certain entity. You can approximate the pH that entity is at from using the different acid-base indicators. Now, you will have to use your data booklet for that, so make sure you have it around and with you. So that wraps up this lesson. Like always, if you need to go back, take a look at some examples, pause, take notes in this lesson, please do that now. Good luck.